And let's talk about the Student Spaceflight Experiments program. So the first thing I should tell you is that um, one of the philosophical objectives of this program is to recognize that all of formal education, all of classroom-based education, has one core goal, which is to prepare our students for the real world. They graduate, they go into the real world. We want to prepare them for that. If you think about STEM education, well, it follows the same path. If we want to inspire some of our students to want to be scientists and engineers, professional researchers, it's critically important that we prepare them for the real world, which means they need to understand what real researchers actually get paid to do. And the best way to do that is to bring a real world experience into the classroom and allow our students to be scientists and engineers right now. And when you ask, well, what do scientists and engineers, how do they do their thing? Well, the scientific method, which is actually a misnomer, because it has nothing to do with science, it's discipline independent. But that's how scientists and engineers do their thing. In fact, that's how the vast majority of professionals do their thing. And the idea is that the process that's used is called inquiry-based, evidence-based learning. It starts with the gift of a question. You look around your world, you open yourself up to curiosity, and you dare to ask a question which defines a personal journey. It defines a problem to be solved. So asking a question is what we mean by inquiry-based exploration. And evidence-based exploration means that you're poking your world to demand evidence and data from the world around you. And the interpretation of that evidence and data allows you to understand how the world works. So inquiry-based, evidence-based learning is what professional researchers do. But we as humans are born to ask questions, and we're born to poke our world, so that we're born to do inquiry-based, evidence-based learning. And I know that some of you are parents, and so you all remember when your kids were first capable of expressing themselves, that's when the unending stream of questions began. And you also, as parents, remember the time that you're looking at your infant child poking their world, exploring near versus far and up versus down and color and texture. And the act of poking their world was the act of demanding evidence in return so that they could figure out how the world around them worked and they can navigate through the world successfully. So we are born inquiry-based, evidence-based learners, which means if you bring a real-world experience from the research frontier into the classroom, students should feel very at home doing that because they were born to do that. And what are the skill sets that inquiry-based, evidence-based learners bring to bear? Well, first, it's ownership in learning. It's not about sitting in a lecture hall and absorbing lots of information. It's ownership in learning. They own the learning experience. They're the ones that dare to ask the questions. And it's problem solving and critical thinking and the ability to navigate an interdisciplinary landscape to secure the core knowledge necessary to solve the problem at hand, and communicating your thoughts and ideas to others so that you can get team think going, which leads into research is typically done by teams. So does everybody understand that skill set that we are trying to nurture here as an authentic experience for the students? Okay. So now, how did we frame a program that delivers on that authenticity? It needed to be inspirational. It needed to be in our area of expertise, which is Earth and space. And so the idea is that we would give PV schools your own space program. And what that means is you're going to get a flight slot to fly one of your student team designed experiments to the International Space Station and have that experiment operated according to your student flight team's protocol, operated by the astronauts. And so they're simply operating as your technicians to carry out that experiment. And each of you, and let me also say that one other aspect of authentic research that we want to capture here is that scientists and engineers need to secure research assets. They need grant money to travel, to buy laboratory equipment. And those assets are typically secured when a federal agency issues a national call for proposals. It could be NASA, it could be NSF or NIH. And the way that they equitably get those research assets out, which is very precious, they're very precious and limited, never enough to go around to all of the researchers that want it. The researchers then respond to that announcement by submitting formal proposals to make the case for why they ought to get that asset as opposed to the other research teams. And if it's NASA, they'll take all those proposals together and convene a review board and strictly grade all those proposals against a proposal evaluation rubric. And the ones with the highest of grades get an award letter, and the vast majority of teams get absolutely nothing. So it is a competition. Real research is done by competition. And what we want students to understand is that they, if they want to become scientists and engineers, will have to be competing for resources. They will have to write real proposals, which are technical documents written against a proposal guide, with embedded citations in the proposal itself and a bibliography of primary references. And so we want to include a real research proposal competition so students get to see the full range of what scientists and engineers have to do. So everybody okay with what I just said there? Give me a thumbs up if you are. Cool. So we're going to give you your own space program. We're going to give you a flight slot to fly one of your student team designed experiments to the International Space Station. You're not competing with any other community because every community has one flight slot to fly one student team designed experiments. So PV schools will have a student designed experiment operated on the International Space Station by the astronauts. But you're like NASA. You have a precious and limited research asset because only one of your student team designed experiments will be selected for flight. And so after you go through a formal microgravity curriculum with your students, you then break your students into formal research teams of 3 to 5 students per team, and you issue a local call for proposals. And all of your teams in absolute secrecy will design a microgravity experiment in a science discipline of their choice and write a formal proposal against a proposal guide to make the case for why that team ought to get your flight slot. So does that all make sense with regard to program operations so far? So let me tell you where the STEM comes from. Each of your teams is going to design a science experiment, a microgravity experiment in a science discipline of their choice, but the design of the science experiment is going to be constrained by the engineering imposed by the flight certified mini lab that must be used. And the design of the science experiment is going to be constrained by the technology of flight operations to and from low Earth orbit. And each experiment is going to be characterized in terms of volumes and concentrations and pH and some kind of well-defined data analysis. So those experiments are going to be characterized through the language of mathematics. So a science experiment designed in a science discipline of each team's choice, constrained by real-world engineering and technology constraints, characterized through mathematics. So does everybody understand how that STEM integrates seamlessly? Okay, so now each team is going to write a formal proposal against a proposal guide, as I said, to make the case for why they ought to get your flight slot. You will then convene a step 1 review board of local STEM educators, PV schools, STEM educators, and local area researchers. And using the proposal evaluation rubric, you're going to grade all of your proposals and select the 3 with the highest of grades. Those are designated your finalists. You send those 3 finalists to us. We then convene the step 2 national review board at NASA, and we will select your flight experiment from your 3 finalists and do the same for each of the other participating communities. And so your flight team now moves forward with optimizing their experiment for 2 months, followed by 4 months of flight safety review at NASA Johnson Space Center's Office of Toxicology, because your microgravity researchers have to go through the same doorways as any professional microgravity researchers, going through a flight safety review to make sure that the experiment does not pose a risk to the astronauts or the vehicles. Now, let me back up a second before I move forward. When we were designing this program, were not focused on the flight experiment. That's amazing, right? One of your student teams is going to have your experiment operated in low Earth orbit by the astronauts. That's real. But our formal STEM objective was to immerse a local community of students in real experiment design, constrained by real world engineering and technology constraints, have them write real proposals against a proposal guide, and go through a formal proposal review process, just like professional scientists and engineers, so they could experience what is expected in the real world from professional researchers. All good with that? Does that sound good? Okay, that all said, your flight team, as I said, moves on for 2 months of optimizing their experiment, followed by 4 months of flight safety review. And then 2 to 3 weeks before launch, your flight team will fill and seal their ground control mini lab and their flight mini lab and ship the flight mini lab to Houston, to NASA in Houston for payload integration. Rhodium, the commercial services provider, will take all of the SSEP experiments across the communities and put them into a single payload, hand that over to NASA in Houston. NASA will carry it to Florida and hand your experiment over to SpaceX. SpaceX will put the experiment in a Cargo Dragon spacecraft on top of a Falcon 9 rocket, and your experiment will launch from historic pad 39A at Kennedy Space Center, the same pad from which all of the Apollo missions to the moon launched and over 100 space shuttle flights. The experiment will be carried 250 miles above the surface of the Earth and accelerated to a speed of 18,000 miles an hour, which is the same as saying it moves 4.5 miles every second. It will rendezvous with the largest spacecraft ever constructed, the International Space Station, which is larger than a football field, and the astronauts will operate your experiment for 4 to 6 weeks on orbit. After that period, the experiments are put back into Dragon for a deorbit burn. They will splash down off of the east coast of Florida, where a recovery ship will pick them up. The payloads will be pulled from Dragon. The SSEP payload will be deintegrated and all the experiments will be inspected and photographed. And then the experiments will be shipped overnight back to the student flight teams for harvesting and analysis. You can send a delegation down to the launch to watch the bird fly, and you can send a delegation to their own research conference, likely also at Kennedy Space Center, because we felt that immersing students in an authentic research conference should be part of this program. The last piece of this is that ever since human spaceflight began, a NASA astronaut crew would work with a NASA artist to create a graphic design that captures the mission objectives. That's what's turned into their cloth mission patch that they wear on their flight suits. And so we'll fly up to 2 mission patches with your flight experiment, so you can open up 2 art and design competitions far beyond just the students engaged in experiment design and proposal writing. You can engage hundreds to thousands of students, it's up to you. And that builds a larger program-wide awareness across PV schools as a school district. And you can open up a competition at the lower grade levels, maybe pre-K through 5, and at the upper grade levels, grades 6 through 12, which means that SSEP is actually an authentic STEAM initiative where you can add A for art. And the other aspect of this is that we have just come out of the 50th anniversary years of the Apollo missions to the moon, the most remarkable journeys the human race has ever taken. We're about to enter into the next deep space exploration phase for NASA with the SLS and the Artemis program. And so here we are right in the middle between celebrating the past and embracing the future. And so history teachers can get involved in the mission patch art and design competition as well. So that's how SSEP works. Does everybody understand how this program operates? Give me a thumbs up if you do. Does everybody understand how it grows organically from that philosophy of approach by immersing students in authentic research so that they can see for themselves what professional researchers are called upon to do? Any comments, any questions before we move on to the next chapter?
Oh, I do have a question. So, does that mean the support for our PV school that's guaranteed? I mean, does not need to compete with other compete for support with other schools district?
Kind of hard to imagine that, right? He doesn't believe what I just said. Did I hear Jeff wrong? Yes, you are not competing with any other school district. Every school district has one flight slot to fly one student team design experiment to the International Space Station.
And can you tell us how many school districts are involved this year?
Well, it's not the number of school districts, it's the number of communities. And
Okay.
we keep that generic because we could have somebody come in from a single large school that wants to do this program. It could be a school district, it could be a 2-year college, it could be a 4-year college or university. And we have been killing ourselves, to onboard communities because this Thursday is the deadline for implementation plans to be approved and letters of commitment of funding to be secured. And right now, it looks like Mission 21 will have 21 communities engaged, where you're one of those communities.
Thank you. That's awesome.
Any other questions?
Yeah,
Yes.
I had a question. So when you talk about the mission patch, does it have to be particular to that experiment, or it's the representing the community and the mission in general?
It's representing your community and the mission in general. So it's up to you. You're going to be, so another way to say this, which I think is very powerful, I kind of said it blandly. I said, we're giving you your own space program. But in reality, the way to say it in an emotional context is that we're inviting all of you, we're inviting all of your students that are engaged in experiment design and proposal writing. We're inviting all of the students engaged in mission patch art and design competitions and the art and design teachers. We're inviting your community into America's space program in every sense of the word. This is not a simulation, which means that you should look at the mission patch art and design competition as a way for students to express themselves as part of America's space program and PV schools' participation in America's space program. Does that answer the question? And Sophie, you had a question too?
I'm not sure if anyone else maybe is the right one to answer. I'm the AVID teacher, or one of them. Is this year's CREST AVID collaboration? Yes. Okay. That's what I had a feeling, but I wanted to make sure I understood correctly. Thank you.
It's always cool when a question can be answered by this. Okay. So now let's move on to the next chapter, chapter 2, Program Critical Timeline and Program Implementation. So keeping with what I said before, I'm going to stop the recording.